Hi all, Matthew Gusdale here again with another lecture on procedural content generation, this time on constraint-based procedural content generation. Once again, as before, this is actually a lecture for the Game AI class at the University of Alberta. So those of you actually in the class, speaking of, can check out these survey links as per the usual. Once again, these will be the way that you get the question answers in for participation points. This will be the easiest way to do that. All right, this seems like enough time. So last time, also known as Monday, we talked about constructive PCG. So constructive PCG, we talked about two major approaches. They were noise, which looked like this. Well, not just like this, right? This is one example of Perlin noise, and I gave an example of a Unity project in mind of trying to sort of recreate the Minecraft-like landscapes with Perlin noise. We also talked about why it's so popular, not necessarily in that order. I'm not quite sure what happened there, but that's okay. We're going to keep going. So why are constructive PCG approaches so popular, especially in comparison to search-based PCG, which we talked about on the lecture before? And then we talked about constructive grammars, ways of basically authoring little bits of content and rules for sticking them together, and the ways that you might have to change how those rules and how those pieces of content fit together to be able to get the kinds of things that you wanted. So the story for PCG generation, PC content generation so far, has been that we either need to iteratively develop a set of tokens and rules for generating and testing. So what do I mean by that, right? So if we're trying to make something, we need to first come up with little pieces of the kind of thing we were trying to make, whether that be chunks of levels, pieces of a song, pieces of a story, etc. And then we'd have to come up with rules for how these things could be combined together. And then we'd have to edit these two things iteratively by generating, seeing how that worked, going back, making changes, seeing how that worked, etc., etc., etc. Or we iteratively develop a way to produce initially random levels, some neighbor function. Now I'm using neighbor function a very broad way to mean both like mutation functions we might see in genetic algorithms, crossover functions, ways of basically going through some space, and a fitness function for generating and testing. So again, same thing. We need to produce some initial random levels, some initial neighbor functions, some initial fitness function, generate, see how that does, go back and change it, etc., etc., etc. So obviously this is constructive PCG and this is search-based PCG. Now, I don't know about you, but that sounds like a lot of work to me. Now, I gave a couple examples of fairly, low impact, fairly easy to put together examples, but I don't know that we necessarily were able to generate anything groundbreaking in those little examples that I put together so far. And in general, trying to get PCG working in an actual game does take a lot of work. In a regular game, when you're making things, you do this sort of generating and testing paradigm, right? But where what you're generating and testing is content that you've hand-authored yourself. Adding in the sort of extra layer of having a generator make that content for you is a bit like trying to, paint a masterpiece by using a puppet on a string to try to do the painting for you, right? So it's just a little bit harder than it would otherwise be. So we can think of either of these options as requiring examples of design knowledge, which we can think of as information about how to design whatever it is we want to generate. So if this is a constructive approach, then that design knowledge is in terms of the chunks of levels and the rules for how those things can combine. If it's the search-based approach, then that design knowledge would be the initial random levels, basically the space that we'd be searching, the neighbor functions, and the fitness functions, where we'd be able to say things like, I think this is good design versus bad design. So here's the intuition of today's approach. What if instead of trying to author the design knowledge for PCG, we had an AI learn it? Now, you might be thinking, hey, I've heard of machine learning before. That's the hot new buzzword that people were using all the time. And yeah, okay, fair. And you might think, oh, well, easy, right? No problem. We're just going to apply machine learning into PCG? Simple. Not so. So let's introduce this formally. So procedural content generation via machine learning was defined by Somerville et al. I will note I'm one of those et als in 2018 as the generation of game content by models that have been trained on existing game content. There's a whole survey on it where we talk about lots and lots of approaches. And there's been tons of examples of PCGML, at least 42 when I counted in January. And these are all kinds of different things, like generating new Magic the Gathering cards, generating novel platformer mechanics, generating rhythm action stages, generating interactive fiction. But very few real, quote-unquote, games have used PCGML, so games you could purchase. Whether that be an independent game or a big AAA, massive studio game. Very, very few of those. In fact, no AAA, but some indies have been using PCGML. So that brings us to our first question. Why? Why do you think that more indie or even, a single AAA game isn't being developed using machine learning-based PCG? All right? Let's take a couple minutes, think this through, write something down, and we'll move on. Okay, that seems like enough time. Let's go ahead and get going. So the big problems that I've at least thought about for why more indie games and why not a single AAA game is using PCGML or PCG via machine learning, there's two big ones. One, machine learning is even more complicated than most PCG approaches generally. So as it is, we were already talking about how if you're a designer and you're working with PCG, I've lost my ability to move my mouse again. I don't know why that always happens. If you're a designer and you're working with PCG, you may not have a lot of computer science knowledge, right? So it might be hard for you to grasp these more complicated PCG approaches. Well, machine learning is an even more complicated version than that. So it's much, much more difficult for people who don't have that computer science knowledge to figure out how do I sort of express what I want in a way that the machine learning approach will learn what I want it to learn. That's tough. And second, machine learning tends to require a lot of training data to be effective. We're talking not just thousands of instances, but millions of instances. Even the most successful video game franchise of all time, Super Mario Brothers, only has, maybe, if we're lucky, let's just say 100 levels per game. And maybe if we're, being generous, we could say maybe there's been a couple dozen Mario games. Okay, we're only up to 2,000 training instances. And that's for the most successful and well-regarded and most popular gaming franchise of all time. So, by default, machine learning just isn't going to work if we just apply it naively. So, what do people try to do? So what I'm going to do is I'm going to introduce PCG-ML for level generation, just because it's been a useful way to talk about PCG-ML, to introduce these concepts, and because honestly, it's where the vast majority of PCG-ML work has been. And we're eventually, but not today, but we are eventually going to talk about 5 different approaches, but today we're just going to talk about one, and that's called wave function collapse. And the cool thing about wave function collapse is it requires only a single training example, which is wild, right? I just told you that for most, for modern machine learning, we're talking about millions of instances of training examples. And with wave function collapse, we can do it with just one. That's wild. And that's why we're talking about it today, and that's why it's by far the most popular of any of these PCGML approaches. It's shown up in the most games. All of them indie games so far, but still, games you can actually purchase. So after that, we have Markovian methods. Again, we're not going to talk about these today. This is just to introduce and get some names on screen. Then Bayesian networks. Then deep neural networks, whether they be things like long, short-term, memory recurrent neural networks and autoencoders. And then GANs. GANs are also a kind of deep neural networks, generative adversarial neural networks, but they're a little bit more complicated because there's basically 2 networks in one for this thing. We can basically think of these as having increasing data costs. So wave function collapse can produce decent output with a single example. Markov models work fairly well with lower numbers of training examples, hundreds of examples. Same with Bayesian, you might need a little bit more for that. And then we get into basic deep neural networks, right, where we can get something maybe if we have thousands, but we really want more like millions of training examples. And then we have GANs. And GANs, you really need a heck of a lot of training examples to get them working. Again, we'll talk about 2 through 5 a little bit later on, but for today, we're just going to be talking about wave function collapse. So I've linked an example here of wave function collapse as it's used in the game Bad North. There's an image here of some cities or some generated houses from this talk. I'm not going to go over this, and obviously we're not going to watch it in this YouTube video. That would be a very strange thing to do, but I recommend checking it out. It's by Oskar Ståhlberg. There's also a really good wave function collapse tutorial as part of ProcJam. This is a much easier URL to go through, which is just procjam.com/tutorial/WFC for wave function collapse. Okay, so those resources out of the way. Let's talk about wave function collapse and how it works sort of broadly. So the first thing we want to do is we're going to extract what we're going to call constraints from our example as x by y windows. So we're going to take little subsections of whatever example input we have, and we'll take that as x by y windows. So if we had a big, say, 34 by 34 pixel image, we might say that's a 2 by 2 window. We're going to grab every single 2 by 2 window from that image. Don't worry, I'm going to show an example in just a second. And if this is 3D, instead we do x by y by z, because you can use wave function collapse for 2D or 3D equally as well. Then, second, we're going to generate content according to these constraints in a standard constraint satisfaction problem. Oh, hey, we talked about constraint satisfaction problem a couple weeks back. Last week? Who knows? Time is strange now. But regardless, we know how to do that. So the major cool thing about wave function collapse is that instead of having to hand author all these constraints, instead we're just going to learn them. We're going to extract them directly from some example. Notably, I'm taking a lot of the content for this particular lecture from the paper Wave Function Collapse is Constraint Satisfaction out of Adam Smith's lab at the University of California, Santa Cruz. There's also a nice, easy blog post version of this paper if you'd prefer to follow along with that. Okay, so hopefully you remember from 2 weeks back, I've just decided, no, a week back, we had a constraint satisfaction problem example where we had these tokens and we had these rules, and we showed how we could generate out stuff that looked like this, right? So notably, when we got to this example, we said, hey, that might not look exactly like we would have wanted. Maybe we wanted something more where like the ground was along the base. There's one mushroom or mushrooms just underground, flowers on top, and sky above that, right? But to do that, we would have had to have changed the rules. We'd have to go back and iterate, just as we were talking about earlier, of doing this sort of generate and test thing. So what if instead of having to author these rules, author these constraints, instead we had a system learn them? So here's going to be our wave function collapse example, starting from our input. So here's one example input. This is something that I've just pre-authored, and I've said, like, this is the kind of thing that I would like to get more of. All right, this is basically what I'm saying. We're going to use a window size of 2 by 2. So that means that for every 2 by 2, so for this one right here, these 4, this 4, these four, this four, this four, this four, this four, this four, and this four, we're going to pull all of these out, and they're going to act as constraints, okay? And so we have a 1, 2, 3, 4, 5, 6, 7, 8, 9 total constraints. So then to begin with, our output starts in exactly the same state as the constraint satisfaction problem did previously, where we have at every single possible position, every single possible thing that could be in that position, okay? Okay, so as before, the very first thing that we need to do is we need to make a decision. So we have to pick one of our possible output locations, one of these slots, and we just collapse down our tokens to just have the one option. So in this case, I just picked at random, not really at random, I picked that there should be a mushroom at this position right here. So what we do from there is we look at how our constraints, now as a reminder, all our constraints are the 2x2 windows we have over here, can percolate through this output, right? So how do they spread through this output? So basically what we can do is we can say, okay, what are all the 2x2s that have a mushroom in them? Thankfully, there's just two. There's this one right here, and there's this one right here. And those are the only two that exist, which means that we know the only valid things that can be to above, to the left, and to the top left and to the left of the mushroom. They can all have to be dirt, and from there we know that the top right, and the right position must also all be dirt. So all of these have to be dirt. So let's go ahead and jump into the implications. Okay, so there's actually a few more than just those, because as a reminder, once we've sort of collapsed down, and that's actually where the wave function collapse names come from, the creator wave function collapse accidentally sort of re-implemented or reintroduced or rediscovered, if you like, constraint satisfaction problems. The collapse is, once we've collapsed, we actually have to then look at the implications of that collapse. So we collapsed all of these down. Now, as soon as we did that, what we did was we looked at, okay, what are things that are allowed to be above the ground? So looking here, right, on all these positions where we have things above ground, we know that we can have ground above ground because of this 2x2. So that's okay. We know that we can have sky or flowers above ground because of all of those, these 2x2s. And so therefore, we know that we can't have a mushroom anywhere else. We also know that there does not exist any 2x2 that has ground on the left side, because there's only these two here, that have ground in the two left slots, that has either sky or a flower in that bottom right slot. So there's only this one or this one, which means that we can only have either a mushroom or the ground in this bottom right position because of this one right here and this one right here, right? In the bottom right one here, there's ground. On the bottom right one here, there's a mushroom. Okay, so those were all the implications. So wow, we massively cut down on the possibilities, right? So let's do another step. So another step means we have to do another decision. Now typically that means that we have to pick the spot that is already the most defined, that has the fewest options in it. And so I just picked mushroom. So we already know that we're going to have like ground here that looks a little different than this one, right? We have two mushrooms instead of just the one, which is totally possible because we have a window size of 2. Okay, so an interesting thing to do would be think about what would be the output if we did a window size of 3x3 instead, or 3x2. Anyway, so let's actually go and look. Okay, well, there's no implications of that because we've already defined everything else that would have been an implication from that. So let's go look at step 3. So for step 3, I actually pick ground to go here. Now that might seem weird. You might look at this input and say, hey, there was no ground at this level, but that's not how wave function collapse works. Wave function collapse works by looking for windows of size 2x2. And there are windows of size 2x2 where we have 2 ground on the bottom and then a ground in that top right position, specifically this one. And so because of that, this is a legal move. Okay? Now, that does have some implications. By making that decision, I've locked in that this has to be ground. And then because this has to be ground, this section here would also have to be ground. Now, you might think that because if we've decided this is ground and this is ground and this is ground, and we don't know what this is, well, there's only one 2x2 that has ground, 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 and then something in this top right. So it has to be ground here as well to match that. And then that same thing happens here as well. So by just making that one decision, we've now said, oh, all of these have to be ground. So I actually could keep going with this. I could have this next decision say there's ground up here, and then it would just be ground all the way through, and we'd have a world of only ground. So that would be valid. That would be a totally fine thing that wave function collapse could output according to the default algorithm. Now, that may not be good, right? That may not be what we want, but the default algorithm would allow it. So maybe you're already seeing why wave function collapse isn't yet more popular than it already is. But that's not what I want to do. Let's just decide for step 4 that a flower should be on this top left decision, or this top left position. Now, what's the implication there? So what are the 2x2s that exist that have a flower in their top left, a ground in their bottom left, and a ground in their bottom right? Well, it's this one and this one, which means, implication-wise, that this can either be sky or flower. Now, that itself has implications, right? Because if we look at what are the 2x2s that have either a sky or flower in their top left, and then 2 ground in the lower section, it's either this one, so there could be a flower rather in the top right, or this one. So there could be, because there could be a flower or it could be the sky, and so it could have a sky in its top right. So we basically didn't really get much out of that decision. So let's make another one. Okay, let's say there goes sky here. Okay, so if sky is here, then the implications, again, would be, let's look at what are 2x2s that have ground on the bottom and then sky in the top left. Well, it's only this one, so this one has to be a flower. And there's already an implication from that. The final implication from that, right, is that if we have a flower on the top left, then it has to be, oh, wait, this is wrong. Because, right, we had a flower in this top left. Now, if we look at this, we can only, because there's only one thing where we have a flower in the top. Oh, no, that's not right. We could have, thank goodness. This is why you have computers do this, not people. Okay, so if we look at this, right, we have 2 different options, 2 different constraints where we have a flower in the top left and then 2 ground below. It's either this one here or this one here. So this top right could still be either a flower or the sky. I chose a flower, and that was the final decision. Okay, so that's one valid output, but obviously there's lots. I talked about some on the way, right? We could have had all dirt all the time. We could have also had something where we had just like this sky and flower sort of pattern repeating a lot. But this is the kind of idea of wave function collapse. By using these local relationships, we can end up getting something that looks quite a bit like that input image. You can even do stuff where you scale up, right? Where we say, okay, well, we're just using these local relationships, so we can have these local relationships go over as far a distance as we like. So it's a very powerful thing. So let's go ahead and look at a Unity example. Now, with this Unity example, I actually didn't write any code, and I'm not going to write any code. I've instead taken code from a great wave function collapse Unity implementation by Joseph Parker, which you can find at this link here. So let's go ahead and take a look at that. Okay, so let's take a look here at what we have by default. What we have by default is a canvas right here. You can see this here. This is our canvas. You can see I accidentally just clicked a bit here, and so I can go ahead and get rid of those. If we look over here on the right, we can see our instructions for messing around with this canvas. You'll note that this is this same Kenny platformer art that we were using previously. So we have a canvas object. That's where we're going to define our input. There's a giant background object, which is just so that this looks a little bit nicer. And then there's an overlap object, which is basically where we're going to generate things out. So, let me make sure that this is all hooked up correctly. That's linked up there. Hello? Oh, okay. That's just gone. That's fine. So, okay, to begin with, let's go back over here, and let's just define an initial scene. So here are our options. Let's see if I can make this a little bigger for us. Boop. There we go. That looks a little nicer. So here's our sort of screen we can work with, this sort of yellow highlighted area. And what we're going to do is we're going to grab from these examples here. So let's grab, say, this sort of top of the ground section. I might grab this sort of bottom of the ground section. Instead of the water icon I was using previously, I'm now using lava, just because I think it will show up a little better. All right, got some lava. And let's get a little bit more dirt. Actually, let's do a higher up dirt. Let's do, I'm just having fun. Let's do one big column of dirt. Let's do another chunk of lava right here. And let's do a little bit more dirt. And that's all that we're going to do for right this second. Okay, so I've done all that. Now, to actually generate things, so let's see, there's our example. Now to generate things, I got to throw this training thing onto here. I've got to reference this training thing onto here. I've got to compile the training thing to say, okay, you've compiled these results. Oh, the width and height are wrong, so we want a 10 by 10. Let's compile these results. Okay, cool, that matches. Then let's go to our overlap. That's over here. It's a light blue, so it's hard to see, but you'll see it in just a second. I hit generate to make a new generation, to do the algorithm, and then I hit run. Okay, so that's not maybe exactly what we thought we were going to get from that example, right? Over here we have just a giant wad of ground, and then down below we have a lava section. So it's maybe not perfect. Let's try generating and running it again. Okay, so that's a little bit more interesting, right? Now we have really, really tall ground, which is maybe not what we wanted. And we have this nice like lava section here. But that looks a little better. Okay, that's pretty nice. That's a little weird. It's just by itself. Okay, this is interesting, right? We have this big, tall dirt thing. We have this dirt thing in different levels of lava. So let's go back to our canvas and mess around with this again. So part of the problem here was we only had content in this bottom section here. So let's go ahead and add some flying enemies up here, which will give us 2x2s in the sky as well. Okay? So let's go ahead and go back to tell our training thing to compile, go back to our overlap, hit generate, and hit run. Okay, so this is maybe a little bit more interesting, right? Now there's a lot of flies, maybe more flies than we wanted, but this is now the sort of right height. What was happening previously was because we didn't have any content up here, any options, empty wasn't considered a valid token, basically. It wasn't the case that, well, it's not that it wasn't a valid token, it's just that we had a lot of empty 2x2s. That all had like the same 2x2, right? If we were all emptied throughout this whole space, then it's the same 2x2 throughout this whole space. But with this, we've given us more variety, right? More variety of things that can go in this empty space. Now that looks really good, right? That looks quite nice, I think. Again, we're getting this very tall thing. That looks better. Very tall thing. Just a wild fly swarm. Looks pretty good. Very tall thing again. So the same very tall things are still possible because we haven't changed this whole section, right? This whole section still has ground, then emptiness above it. So we can still have these very tall sections that have emptiness above them and then ground. Let's make some tweaks here and see what happens. So part of what we had was I've got to click on the canvas. Part of what was happening here was I had a fly right here, right next to the ground. So if I don't have that, let's go back here and see what implications that has. Doing a lot of these. We're getting a lot of these really, really tall ones again. Some of the shorter ones as well, but a lot of the really tall ones. So part of the problem here is that wave function collapse, right, is not directional. It has no notion of top and bottom. It only knows about these hyperlocal 2x2 little relationships. Okay, so let's try changing this. Let's try changing this 2x2 to instead be a 3x3. So I'm gonna hit this this n here and change it from a 2x2 into a 3x3. And let's try to just go ahead and generate some output, but now using 3x3 windows instead of 2x2 windows. So, nothing seems to be happening, huh? Don't seem to be getting anything, huh? There we go. Okay, so I just had to hit that a lot of times, right? Before we finally got something. And what was happening there, though this implementation doesn't give me an error or anything like that, what's happening there is that it is much, much harder to be able to get a output that has a 3x3, all the 3x3 constraints satisfied. So basically, it's possible to get into a state where it's no longer possible to generate output that is valid if we're using 3x3 constraints. So it's way, way, way harder. So anytime that it's breaking like this and not showing anything, that's because we just can't find anything. We got stuck somewhere. There we go. So here, this is another technically valid one because we have this 3x3 and this 3x3 and this 3x3, etc. So I'm going to go back to 2x2, and immediately this is going to be way easier to generate, right? Now, what happens if I set this to 1? Right? If I set this to 1, we have 1x1 constraints. So as long as one of these tokens is the same, then it's valid, which basically means that we're just going to randomly pick from our possible tokens or our possible things here, and they're just going to randomly pick for each slot. So there you go. So we can see the impact of that constraint window size. Too big, and it's impossible to be able to actually solve the problem. It's not impossible, it's just much harder. Too small, and it's just random noise. So another thing that I told you that we could do with wave function collapse is actually produce output of a larger size. So what if I change the width of this thing from 10 to 30? And then I hit generate and run again. Check that out. Now, if this was a platformer level, this would be totally insolvable because of the massive chunk of lava. Again, there's no way to ensure solvability here. But we can get all kinds of, nice long levels this way. So maybe we think, oh, okay, well, part of the problem here is that our example, we don't just have enough of stuff here. That's why we're getting sort of some bad output, like this massive section through here. So let's give it a little bit more detail, right? So let's expand our canvas to a 12, 12 by 10. There we go. And let's go ahead and make a few other changes. So we have a lot of flies right now. Let's actually cut down on our number of flies. And I'm going to add a snail here. Boop. There we go. Just a nice floating snail. And I'm going to add a sign here, a fence there. And then I want to add, a sign. There we go. And then let's go ahead and make this a slightly different height. Okay? So here's our new example. So let's go ahead and retrain. Okay. And let's go back to our output, or overlap rather, and just generate some more stuff. Okay. So a few things to note here. First of all, we have a fence that's right next to this sign again. Let's do this again. No fence, no sign. A fence right next to a sign, a fence right next to a sign. So this is actually really cute. I like that. So by the fact that we've put the fence directly next to the sign, and the fact that we're using a 2x2 means that we always have to have fences next to signs. Now, if I give this one more example where I say, let's go back to here, and I give an example of a fence, all by, not all by itself. Let's do, there we go. A fence all by itself, not next to a sign. And we retrain. We go back over here. Now it's going to be possible. Oh, hello. Look at that. Now we've got our fence and sign thing again. Want to get a fence by itself? Come on. There we go. It's possible now to get a fence by itself. Now, if I did something instead where I said something like, let's see here. Maybe if we did something where we always had we possibly had a fence next to a snail, or rather, a snail always had a fence to its right. Go back to our overlay. Oops, I forgot to train. Go back to our overlap, hit generate, hit run. And we can see every time we see a snail now, we're going to see a fence to its right, but we can have fences by themselves. This is why we got a lot of fly variety, by the way. It's because we had a lot of flies, which means that we could put flies in a lot of different places. Here's one where we have all three of these constraints hitting us all at the same time. So by having more uses cases of each of our tokens, right, more times they show up, that gives our wave function collapse more constraints to work with, more valid ways that these tokens can be placed next to each other. So, for example, what if I went ahead and I added, let's say did that work? Hello? Oh, I have to, gotta click on the canvas. No, that wasn't right. There we go. If I put a snail up here, right on top of this column, and we retrain, let me go back over here. Now, again, it will be possible to have snails all by themselves, like you can see right here. There we go. See, now we have snails all over the place. Oh gosh, maybe too many snails. Maybe too many flies. Lots of stuff going on here. Okay, so hopefully that gives you a pretty good sense of how wave function collapse works, the ways that you can tweak the input to be able to get changes in the output. Now, as a reminder, we were never able to fix the solvability problem here, right? We could never create output levels for our platformer game that were always solvable. So that's a thing we're thinking about. But hopefully in general, this gives you a sense of how you can work with wave function collapse and how, by looking at our output, we're doing a similar kind of generate and test. But what we're sort of making tweaks to in between the generate and test is what our input is. Okay, let's head back to the slides for now. Okay, and we're going to go back to the slides directly into a question. So here's the question. Given everything you've learned now, why aren't more video game developers / designers using wave function collapse in their games? Okay, take a couple minutes, give it some thought. Maybe I've been hinting at it for quite a while, but give it some thought, write something down, and then we'll jump back in. Okay, that should be enough time. So there are still problems, right, with wave function collapse, which is why it's not used by more people. So one big one is controllability. Since the constraints are learned, it's possible that the wrong or insufficient constraints will be learned. So, right, there was no way for us to specify we wanted playability. It did the dang thing again. Please let me have a mouse. Thank you. Now, but this could be, this could be something for a lot of games. Generally, it's going to be the case that if there's like global constraints that we need to worry about, we're not going to be able to learn those because, again, all we care about is the 2x2 windows. So, like for a puzzle, it's not necessarily true that a puzzle will be able to, will be able to be solved or will have just one solution. If we were generating, people, if we were actually, that's an interesting idea. I wasn't thinking about that at all, but let's try to generate a person. Let's take a look here. All right. Open up wave function collapse example again. Okay. So I think this is going to be broken again. No, okay, it's not. All right. So here was our earlier example, right? I'm going to shrink this back down to 10 by 10. Okay. Let's go ahead and just make sure that everything is like working. This is all Gucci. Yes, cool. Okay, so let's go back to our canvas and let's get all of this. Oh, actually, wait, I forgot. I can just clear. So let's go ahead and try to draw a person, right? This is just, just a little pixel drawing tool. We can basically think of it like that. Let's try to draw a person. So I'm an excellent artist. So here's my great person. Oh God, this is already really bad. Okay, here we go. Okay. Little arms on this person, and then a little head. Oh God. Okay. All right. Well, that's not great. Maybe. Let's see. How do I make this look more like a person? Give them eyes. Now they're an alien. Okay. There we go. There's our giant blockhead person. Let's try that again. So, given this, what do you think are the chances that our person is going to look like a person on the other side? Well, let's find out. So I'm going to go ahead and, we lost our training thing because I cleared it, I guess. Let's go ahead and add our training thing back on. Please give me this training thing. It's a 10 by 10. Overlap has to reference the training thing. Go back to this, compile the neighbors, and go over to overlap. And let's take a look at what we get. Generate and run. Don't mind if I do. That sure doesn't look like a person. Generate and run. Generate and run. So for something like a person that has a lot of global requirements, right? We have to have arms that are located here and a head that's located roughly as far as the arms. This 2x2 is not gonna cut it. Now this is something where maybe this would work for our 3x3. Let's take a look. No. Okay. Yeah, we just don't have enough variety for a 3x3 to work either. So here's a really easy example, right? Where because this figure, this thing we were trying to get it to learn is just too complicated, has too much, well, specifically, it has too much global requirements, too many things that have to be globally true. We have to have just 2 legs, just 2 arms, etc. It's very hard for us to learn to output something like that. Now, we can make it a little bit easier if I use, for example, unique things for like the arms and legs. So let's see, if we go back to canvas, let's say that the arms are always this token. It doesn't matter that they look the same, similar as these dirt tokens, because each of these just has a unique ID. Let's say that the legs were always fences. No. Always fences is what I wanted. Please go with the fences. There we go. Let's say we had beautiful, instead of this orange, we had beautiful pink snail eyes. Okay, and then maybe we have for our head, we have our nice, oops, didn't mean to do that. We have a nice orange head. This is not a political cartoon. Okay. So let's see what this does. So let's go ahead and compile and train it, and then go back to our overlap and try to generate and run. Well, that didn't work either, right? So again, just the fact that we have, okay, now this is getting closer, right? We got a whole head. But just the fact that it's a 2x2 makes it really, really hard to be able to learn, ooh, nice long legs. Okay. Again, 3x3, it's going to be very, very tough to be able to generate anything. Okay, that feels like enough. Let's head back over here. Okay, so on to the second. So, notably for controllability, here's a real-world example. So, Caves of Cud, which is a game, it's an indie game. You can download it on Steam right now. Its designer, one of its two designers, Jason Grenblatt, who is primarily responsible for its use of wave function collapse. There's an example over here on the right. Use an additional pass over generated levels to ensure that the generated levels were correct, right? So in this case, they were generating landscapes, like, world maps, sort of. So they did some checks to make sure that the world map made sense, right? That you didn't have things like mountains broken up by an ocean. Well, maybe that would make sense. It's like the Pacific Islands. A city in the middle of an ocean. That might make sense for some games where you want to do like an aquatic city, but it wouldn't make sense for their specific use case. So they did some extra checks to make sure, hey, that's not going to be possible. That's not an actual one in the game, but just an example. And then complexity. People, especially designers, tend to think about design as being based on a series of X by Y windows, or in the case of a 3D one, X by Y by Z windows, right? So it's even harder than for other PCG approaches to think about this, to conceptualize working with this, and to understand what it's learning, why it's not learning what you want to, et cetera, et cetera, et cetera. So we're going to be skipping a lecture on Friday. That's because the people actually in the class are getting a quiz. Everybody else who's just been hanging out and watching these videos, you just got a day off. Congrats. But on Monday, we're going to cover all the other PCGML methods that I mentioned down below and why they aren't ready to be used in game development yet. So what's keeping them from being used in game development? I will talk to you then.